Good morning, everyone. We're going to be starting here shortly, just waiting on some more people to join us. Good morning, everyone. We're going to go ahead and get started with today's webinar. Welcome to the webinar on Pathways to Smart Manufacturing through Smart Maintenance. My name is Amy Jordan, and I'll be your host for today. Let's look at our trivia question. What percentage of the manufacturing costs are attributable to maintenance? If you chose C, 15 through 40%, you are correct. Reducing our maintenance costs or the effects of unplanned maintenance should be on each of our to-do lists. I have a few housekeeping items to cover before we get started. All attendees are automatically muted with their camera turned off. If you have any technical difficulties accessing or hearing the presentation, use the chat pad and we'll try to correct them promptly. Attendees can submit questions at any time during the 40 to 50-minute presentation using the question and answer button. However, we'll wait until our question and answer period at the end of the webinar to answer your questions. This will allow us to move through the material more efficiently. If you have any questions after the webinar is over, please send via our email to pentap@psu.edu. This webinar is being recorded, and we will also be uploading this webinar onto the PennTap website. All attendees will receive a follow-up email notifying you when it is available. On today's webinar, we will have a guest speaker from Penn State's Department of Industrial and Manufacturing Engineering, Penn State faculty, Vittal Prabhu. Dr. Prabhu is professor and Charles and Enid Snyder Faculty Chair in Service Enterprise Engineering. He received his PhD in mechanical engineering from the University of Wisconsin-Madison. Dr. Prabhu works in the area of distributed control systems with a focus on manufacturing and service enterprises consisting of discrete events, physical processes, and service processes. He teaches courses in manufacturing systems, service systems, and distributed controls. And again, my name is Amy Jordan. I'm a technical advisor for PennTap's Energy and Innovation Services. My role is to help build and manage relationships between small and mid-sized companies in Pennsylvania and Penn State. In our webinar today, we will be discussing ways in which PennTap can help identify no-cost and low-cost ways to improve your business through our direct technical assistance, referrals to our resource partner network, and engagements with Penn State students, faculty, and facilities. Dr. Prabhu, who will then present pathways to smart manufacturing through smart maintenance. We'll end with question and answer period. So let's get started with a little bit about PennTap. The Pennsylvania Technical Assistance Program at Penn State, known as PennTap, is a statewide technical assistance organization charged with supporting Pennsylvania businesses and anchor institutions, including manufacturers, municipalities, educational institutions, entrepreneurs, and economic development agencies. We began over 50 years ago as one of the first technical assistance programs in the country. PennTap focuses on helping Pennsylvania businesses through two primary areas of expertise: energy and environmental services and innovation services. Through these pillars, our goal is to help your business be successful and drive economic growth in Pennsylvania. You can find us at pentap.psu.edu. PennTap has a diverse staff with backgrounds in chemical engineering, electrical engineering, and environmental science. Our staff includes a certified energy auditor, certified energy manager, registered environmental auditor, renewable energy professional, and a Six Sigma Green Belt. Through our energy and environmental services, our technical advisors perform pollution prevention and energy efficiency assessments, also known as P2E2 assessments, where we help you to decrease pollution and increase energy efficiency at your site. The E3 assessment builds on the E2 assessment by incorporating lean manufacturing into the process. And energy management systems will provide your company with a framework to integrate energy efficiency into your existing management systems. And building retuning offers those involved in building operations a low-cost approach to energy efficiency. We offer opportunities to Penn State graduate students in the College of Engineering to gain real-world experience by having them assist us with our energy audits. They utilize the knowledge they're gaining in the classroom to bring new ideas to our clients. And again, we go beyond energy as we also work closely with our clients to understand their needs and improve their innovation. Through our innovation services, PennTap can provide your business with no-cost and low-cost opportunities to engage with Penn State students, faculty, and facilities through internships, classroom projects, and capstone courses. We've assisted in identifying opportunities for internships, not only for our engineering students, but also for business-related disciplines, agricultural interests, and other colleges within Penn State. The Penn State classroom projects and capstone courses provide great opportunities for companies to tackle real-world problems utilizing classroom knowledge, tools, and world-renowned facilities. For example, further product development through prototyping at the Learning Factory, improved production flow through Six Sigma student projects and an IME classwork, and growth into new markets with market research completed by our Smeal College of Business Nittany Lion Consulting Group. PennTap maintains relationships with a wide range of resource partners throughout the state as well. These resource partners bring different tool sets to assist your companies outside of what PennTap directly provides. Our resource partners include small business development centers, industrial resource centers, Ben Franklin Technology Partners, local development districts, workforce development organizations, and others. Our relationships with these partners are vital for Pennsylvania businesses. The Small Business Innovation Research Program is a highly competitive program that encourages domestic small businesses to engage in federal research and development with the potential for commercialization. Through a competitive awards-based program, SBIR enables small businesses to explore their technology potential and provide the incentive to profit from its commercialization. PennTap's direct connection with Penn State research allows us to make the right connections to faculty for small and medium-sized businesses to meet the requirements for university participation on this program. In 2020, PennTap helped 105 companies in 36 counties throughout Pennsylvania to save a total of $2.5 million. We helped to create or save 29 jobs. As I mentioned earlier, one path to innovation that PennTap follows is making connections with Penn State faculty and their groundbreaking research. I'm now going to turn the webinar over to Vittal Prabhu, faculty at Penn State, to discuss pathways to smart manufacturing through smart maintenance. Thank you so much for joining us, Dr. Prabhu.
Thanks for the introduction, Amy, and thanks to PennTap for giving me the opportunity to present our work. I'll be presenting work done in collaboration with two of my graduate students, Rakshit Badrinath and Kaivan Jain. They're both doing their PhD in industrial engineering in Penn State, and Casey Morris, with whom we collaborated from National Institute of Standards and Technology. So what I'm presenting today is part of a larger effort that we did with NIST, and is also part of the dissertation work of the two students on this project. Next slide, please. So before going any further, I would like to gratefully acknowledge that this was funded in part by NIST, as well as the collaborations were made possible by IMC, especially Dana Gordon, who initialized the collaborations with SMEs within Pennsylvania. And I'll be presenting some of the results from those collaborations. So the outline of the talk today will be really, how do we navigate a pathway to smart maintenance? We will try and answer three questions that we found pertinent in discussing with several small companies in the region. Should a company embark on smart maintenance now? How should the company prepare for such a journey? And what are the costs and benefits at the factory level? We hear a lot of buzz and hype, perhaps, in terms of smart manufacturing, Industry 4.0, IoT, AI, machine learning, big data, so on and so forth. So what we're trying to do is get our arms around this problem in the context of small manufacturers and try to put some numbers together in terms of what are the costs and benefits. We know several large Fortune 100 companies have deployed these technologies and obviously benefited from them. How does this change in the context of smaller companies, especially because they may not have the same human capital? So this may be a point where PennTap could play a very important role in helping SMEs in our region. So we'll try to answer these broad questions through case studies that we did working with 3 manufacturing companies in the area. I'll keep the discussion at a fairly high level. I promise that I won't show you any equations, and we'll try to save some time for Q&A towards the end. Next screen, please. So the pop quiz that Amy had indicated that typically manufacturing companies expense about 15 to 40% of their costs are attributable to maintenance. And of course, this varies across sectors, as you can see in this pretty busy chart. There are all kinds of maintenance costs ranging from transportation, mission critical infrastructure, and we are talking primarily about discrete manufacturing in the present context. In addition, over 30% of the workforce deals with maintenance in some form. And the amount of money that companies need to spend on maintenance is increasing over time because the equipment that are deployed on the shop floor is getting more sophisticated, more complicated, and that's one of the reasons why we need to pay particular attention to this problem. So the reason maintenance is important for any manufacturing operation is that it has a snowballing effect. And if you take a really big picture view, every company needs to have some form of maintenance strategy that impacts the availability of their equipment, especially the bottleneck equipment on their floor. This in turn impacts something that we call effective process time of the equipment. And I'll explain this in a minute. And also impacts the cycle time. So if your machine is down long periods of time, then you will have longer cycle times. In order to compensate for it, you probably end up having more WIP in the system, so on and so forth. So this is the kind of snowballing effect that we see when maintenance is not done very well. And bottom line is it impacts the manufacturing system throughput, therefore total revenue that you can get from the system and the profits that you earn. So central to all of this, if there's one takeaway, that is this notion of effective process time. We'll keep this fairly simple and try to build some intuition around it. Maintenance affects what we call the effective process time. So if this blue box here is some equipment on our shop floor, could be a CNC machining center, could be a 400-ton press that is pressing out parts or whatever you have, okay? So parts arrive, wait for the machine to become available, then it gets loaded, gets processed, and then parts depart. This is typically the way in which parts flow through from one work center to the next. So once it departs from here, it goes to maybe the next work center and then perhaps gets shipped finally at the end of the line. What happens is you can these equipment here can experience random failures. And this is what we can try and counter with smarter maintenance. Now, what is the consequence of these random failures? I'm going to try and illustrate this with one little cartoon here on the right side of the slide. Let's suppose in the ideal world, if we did not have any such random failures, and if you stood there with a stopwatch and you measured how much time this particular piece of equipment took to process parts, and you plot the histogram or a distribution, you might get a bell-shaped curve like this blue one with a very narrow spread, okay? That's the term that we use to describe the natural process time. So the key point here is that the spread or the variance of the natural process time is relatively small in most manufacturing processes, okay? However, when such processes are corrupted because of random failures, then what happens is the same distribution, instead of being a narrow spread bell curve, now is much more widely spread. And this has a lot of adverse consequences. So the distinction here is this blue curve, when subjected to random failures because of poor maintenance, leads to a wider spread of what we call effective process time. So if you think of cascading effect, what happens is the cycle times of parts inflate, the throughput starts to go down, and it hurts the bottom line of the companies. There are lots of other consequences. You won't be able to predict as easily how long a part is going to take, and you start quoting inflated due dates to your customers. So there are lots of consequences because of these random failures. This is one of the causes of variation or variability in manufacturing systems. So the key takeaway is, how do we reduce this? Okay, so if we knew that the machine is going to fail ahead of time somehow, then we can schedule its maintenance and repair, maybe when it is much more convenient, maybe on the third shift, which is not functioning. Maybe we are running the shop 2 shifts a day. So we could use the third shift to do the maintenance, so it doesn't really take away any capacity from our system. And if you know something is going to go down ahead of time, then you can actually plan to do that activity in a much tighter way. And your repair times will be more predictable. And all said and done, this red curve here, the effective process time, can be expected to have lesser spread or lesser variance. I'm sure most of you on this call have heard of lean manufacturing. This in nutshell is lean manufacturing. The wider the spread, fatter the manufacturing is, narrow the spread, leaner the manufacturing is. So another way to think about it, if you're familiar with lean manufacturing, is by employing smart maintenance techniques, we'll essentially end up making our manufacturing systems that much leaner. And that's what is motivating the rest of this talk. So let's think about what are some of the common maintenance strategies used in industry. So you could have planned maintenance. Periodically you shut down the plant, check everything, overhaul your equipment and such. So this period when you do it can be essentially time-based maintenance, maybe once a month, once a week, or do some small things every shift or between shifts and such. So there are many ways to do this. Lots of literature and practices built around TPM that does much of this. And there's also predictive maintenance, which is what we'll be talking about. If you can employ some of the technologies that are becoming more affordable and more commonplace, such as sensors that can be quickly installed on your equipment, you can actually predict the health of the machine and make decisions proactively so that we make our systems leaner by reducing the spread of the effective process time. The worst case is you make strictly corrective maintenance, you let the machine run to failure, and once it fails, then you fix it, okay? So that would be the other extreme compared to predictive maintenance. So the consequence of any particular strategy or the combinations thereof that a company uses impacts several key performance metrics: equipment availability, equipment utilization, and of course, effective process time. So as I indicated early on, there's a lot of money that is being spent, and this is increasing in terms of maintenance and being able to sense the health of a machine. That is becoming very interesting and important going forward for a variety of industries, especially manufacturing. And you will see in almost any trade press that the use of Internet of Things, especially sensors that can be connected to the internet, are gaining a lot of ground. And this is one such infographic that explains that there is at least $100+ billion spent just on IoT as we speak, and probably increasing far more as we come out of the COVID pandemic. Also, companies are moving away increasingly from run to failure to predictive maintenance so that they have less adverse impact of a machine going down, and they can be much better prepared. I won't try to read through this busy slide. It's a report that was put out by PwC. We've shared the link here. If you're interested, you can look that up. But essentially what we would like to convey here is that there's a lot of technology that has now come to fruition that is accessible and affordable for companies of practically any size. And if you haven't done so, you should pay attention to these technologies. And if you need resources to go about doing this, please talk to one of the Penn staff advisors. They might be able to help you get started. So how should a company navigate its path towards smart maintenance. And from our perspective, we will try to address this question, address this by answering three questions. Should the company even embark on smart maintenance now, given the state of its infrastructure and the state of its operations and practices in their operations? And depending on the outcome of that particular question, how should the company prepare for this journey? Maybe the company is pretty savvy in terms of how it collects data and how it runs its operation. Then it has a particular path to get on to smarter maintenance. If not, then maybe there's some other pathway or a detour for this in this pathway, and we'll talk some more about this. And then finally, what are the costs and benefits at the factory level? Can a company get a reasonable estimate of the costs and benefits before really biting the bullet and committing to making major investments in this? This is really what we want to share with you, and we will share our experience in terms of the kind of tools that we have built based on the engineering models for manufacturing systems. So here's our depiction of the pathway to smart manufacturing through smarter maintenance. So working with companies, here's what we figured would be a good course of action. First, we understand the processes and material flow for a particular company. Collect data. Companies have varied infrastructure for this. Some have sophisticated software that collects data. Some have just maybe a hunch based on experience. Others note down on paper and pencil what's happening in the shop. And there's a whole spectrum of possible data collection strategies. But once you have the data, what we can do is use one of our readiness analysis technique and figure out whether the company is ready or not. And this blue box here is where Penn State's engineering talent can come in handy. You don't really have to go wire up new sensors. Based on the data, we will construct a model that can reside on a spreadsheet of some sort. And we'll try and predict what the performance improvements might be if we employ better maintenance strategies. If not, if a company is not ready for smarter maintenance, then we'll tell what may be the better course of action to do before you get on to smart maintenance. So that is this detour steps 3A, 3B, and 3C. So if a company is not ready, then develop a pathway for improving the manufacturing system using something like lean manufacturing. And based on that, calculate the return on investment for lean improvements. And once you have a system that is reasonably lean, and the operating word is reasonably lean, then the company becomes ready. And then you say, well, if I now go ahead and try and invest in condition-based maintenance using these IoT sensors, what will be the potential return on investments that I can achieve as a company? So we want to assess the business value of going down this path. And then do a small pilot so that employers and the employees and the management of the company get comfortable with these technologies. Develop a predictive maintenance model based on the experience that you gain, and then go for a full-fledged IoT-based, condition-based maintenance solution. So that will be our pathway for getting towards smarter maintenance and thereby achieve one of the components of smart manufacturing. So the green segment of this pathway would be for companies that are well prepared and are ready to get towards smart maintenance. And the red ones are detour that some of the companies that are not ready would need to improve their operation and then come back and revisit the problem when they are better prepared. So how do we go about assessing this and decide which fork in the road that a company should take? So we have roughly 4 broad steps. I won't go through each one in detail, but I'll give you a high-level sense of what this means. So first step is we do something called internal benchmarking. Based on a few key parameters for the manufacturing system, like what's the natural process time in your system? This is something that practically every manufacturer should be able to tell. And we will walk through the company to get this information. Identify the bottleneck rate. Everybody knows what the bottleneck is. You can see it typically by the WIP that is stacked in front of it. Figure out what's the current WIP and the current throughput. Based on these handful of data, we can try and model how the current performance is for the manufacturing system. And based on that, we go to the next step where we sort of dissect what really happens in the system that leads to downtime. So typical sources of data for that are production reports or downtime reports. And here the key question is, how much of the observed downtime is due to random equipment failures? And this is really one of the key factors that leads to which fork you take in the pathway. If much of the downtime is caused by something else, such as setups or teardowns that you have to do to change over from one type of product to another type, then maybe you need to focus on how you reduce the downtime caused by setups rather than focusing on maintenance at this point. Okay, so that's really what this step focuses on. And then next step is the maintenance time analysis, where we look at sources of data like maintenance time work orders. What are the documented maintenance reports? Now, this varies from company to company. Some have it very sketchy, some have very detailed reports. The question that we really want to answer here is, what are the key components of the maintenance activity that can be reduced through the use of condition-based maintenance? Let me kind of flesh this particular issue out. Suppose you have a particular piece of equipment whose spare parts require about 2 weeks of lead time, which means once it goes down, it'll stay down for 2 weeks because it takes you that long to get the spare parts to put it back together and get it back to operational status. So we need to look at what are the components of the maintenance activity that constitute the downtime to say, hey, if you did go for condition-based maintenance, what might be the bang for the buck that you get from it? Okay. And finally, based on all of this, we come up with something called the readiness evaluation, and then say, hey, should the company embark on a pathway towards smart maintenance now, or should it go back, fix some of the basics that are there, which might be lower hanging fruits based on the current operation before getting on to the maintenance problem? And this does happen in some companies. And I'll share examples of both sides of the fork. So next I'll talk about case studies that we did with 3 companies. They are from different types of manufacturing verticals. One is a paper company that made paper products. That they had a strategy of really run to failure. They would let the machine run to fail, let it fail and then fix it. So the machine would be down till they got the spares and got the maintenance techs to fix it. There's a plastic company, again, same issue, and they had fairly long lead times to procure the spares. The third one was sort of a sintered metal company. They did have preventive maintenance, and they had a more sophisticated operation. So these, one thing is these acronyms that we coined for these companies are fictitious. We don't want to share the actual name of the companies. So we just call them PMC, PPC, and BMC. The names do not really matter for our purposes here. So here's what we found. working with PMC. So let me explain what this chart is. On the horizontal axis, on the x-axis, is the work in progress or work in process in terms of paper rolls in this case, and the throughput in terms of rolls per hour. Okay, so the internal benchmarking tells us that if the company, the best case that the company can achieve, it will be along the blue curve. Okay, so if the company was doing really fantastic in terms of its performance, then you pick the number of WIP paper rolls they had. Let's say they had 6 paper rolls, then they would be very close to this throughput. That is something like 125 rolls per hour. Okay. Now that would be the sort of upper bound or the ideal, theoretical ideal. So no manufacturing system in real life would achieve that, certainly not this practical system. So the practical worst case would be this gray curve here. So this serves as our benchmark. So what this means is if we had on an average 6 rolls of WIP in the system, and the average throughput was, let's say, 110 rolls per hour, then we'd say, hey, this system is doing better than the practical worst case, which means it's doing pretty good. If, on the other hand, the throughput was much below the corresponding gray point on the gray curve, then we know that, hey, there's lots of opportunity to improve. So a good way or an easy way to think about this is if the performance in terms of the throughput is above the gray line, then the system can be considered to be relatively lean. If the performance is below this particular gray curve, then you can consider the system to be relatively fat. Okay, so there's opportunity to improve. Maybe you can work with PennTap to do a lean project and see how you can get closer to this gray curve in terms of the performance. So this chart was showing for particular process parameters for the paper mill, how the throughput can vary as a function of WIP. And these are the bounds between these orange line and the blue line. And depending on where the actual performance is, we can tell whether it is good or bad. So in this particular case, the throughput was 71 rolls. It's way to the right side and way close to the worst case. So we know that for this particular system, there's a lot of opportunity to improve and get better in terms of the performance before they embark on investing any time or resources in getting better with in maintenance. Okay. So the second company in our case study is plastics. Notice here the units of work in process and throughput are different, but mathematically, it's very interesting to see that instead of being so far out on the right side and close to the worst case, this company is now pretty close to being lean. Okay, not quite there, but it's very close to being lean. Okay, so maybe it's almost there or quite there. So if we do some improvements by looking at the downtime, maybe we can tell, hey, what you should do differently to improve your performance. Okay, and get closer to this blue point here at the, if you look at this coordinates, it's 8 and 0.09. So 8 gives it this and 0.09 gives it just below this gray line here. So maybe we can push it up here by doing some lean manufacturing projects. So this third company is the baked metals company. And of the 3, this one was clearly the lean one in the sense that if you look at the chart, same sort of notation for the amount of WIP they typically carry, their throughput exceeded the practical worst case, and it was actually getting towards the best case. It won't get to the best case, but it is getting towards the best case. So this looks like the sort of manufacturing system which could clearly benefit by improving the maintenance operation and takes the other side of the fork. So we did the internal benchmarking for all three companies. And next step, we do downtime analysis. Look at what are the causes or what are the sources that contribute to downtime. Typically, three major sources of downtime. One is setup, to change over from one type of product to another type of product. Planned maintenance, if you have to do something to your equipment to get it in shape to churn out products, that's planned maintenance. And then you have unplanned maintenance when something goes wrong. Now, what you can see here is for the two companies on top of this chart, close to 90% was because of setup, okay? And some 12% was because of unplanned maintenance. Whereas for the third company, unplanned maintenance contributes about 45% of downtime. So just eyeballing this chart, you can see that, hey, there's a lot that can be potentially gained if you can reduce this 45% of unplanned downtime using condition-based maintenance and look at some of the newer technologies to be more proactive to improve the performance. So we can get into the weeds in terms of what really happens when a machine goes down and what is the benefit of going with condition-based maintenance. So I won't go through this fairly busy slide, but the key thing is you get advance notice of when a machine might require to be repaired, and you can plan proactively and reduce the time from being this large to something much smaller. Of course, the scales vary depending on the type of equipment and the nature of the lead times involved, either in repair or procuring spares, et cetera, et cetera. So, but this is the overall concept. When you employ condition-based maintenance, it offers prospects of reducing the downtime on your equipment, and that in turn leads to significantly improved performance. So we have a readiness evaluation benchmark that looks at all of these things, and based on it, if it reaches a particular threshold of 10 out of 16, that's how we score it. If it reaches at least 10 out of 16, then we say, hey, this company is now ready for investigating or investing in smarter maintenance or condition-based maintenance because they're fairly lean otherwise, so we can get more from the system now by being better at maintenance. And we can actually visualize this and get a sense of where the contributions might be, so the management can make a much more informed decision before really even investing in any sensors. The companies that are not ready for smart maintenance, there are various steps that they can go through. Typically, much of the downtime is caused by setups. You standardize setup, standardized process, standardized maintenance, raw material flow standardization, try and adopt preventive maintenance practices, and then finally get to condition-based maintenance. That will be the way that companies that are currently not ready will embark on smart maintenance pathway. So using the underlying mathematical model, we can actually estimate for each stage what will be the savings in terms of cost savings, really, as you evolve through this step, and you can try and put some dollars and cents to estimate what will be the net benefit, and decision makers can then decide whether it makes sense to make this investment. Similarly, you can make and you can analyze in terms of performance, how cycle time reduces, and what is contributing to it. So you can make a much more objective, clearly informed decision. So for companies that are already running quite well, you can take the underlying models that we build. You can look at how many sensors you can deploy and what will be the cost for that. So you can actually calculate based on price quotes that you might get from vendors, what is the total cost and what will be the resulting benefit in performance depending on how condition-based maintenance affects. So you can focus on critical machinery or bottleneck stations based on what the models indicate or based on manager's experience. So if you have the model and you can study it, experiment with it on a computer, on a spreadsheet-like interface, and get a much better resolution to gut instincts on how to go about getting smarter in terms of manufacturing operations. So this is a particular case that we talked about for the BMC. So the key point here is you can analyze what will be the consequence in terms of benefits in improved throughput. Last but not the least, how does it impact the bottom line? So here's an example of an analysis that we do with the Dupont model. So we can look at what is the current throughput or the baseline throughput, what is the potential throughput. Clearly, throughput can be expected to improve when you have condition-based maintenance because now you have shorter or lesser unplanned maintenance. So this is where the engineering models plays a crucial role. That is in our ability to predict what this might be. I also want to emphasize that these are model-based predictions, so they're only as good as the models and the data that is going into the model. Nevertheless, you get an objective way to assess the impact. So based on the throughput improved and profit earned per part, these are fictitious numbers. You can change it for the particular company at hand. Excuse me. You can calculate the impact on the profit margin. Okay, so that's one side of the Dupont model. The other side is it changes your cost base. You have to now procure some capital equipment in terms of the sensors and the base stations, so they cost you some money. These are indicative numbers. And then you have to hire technical services people to install the sensor for you. There's installation cost. So all of that adds to capital cost for you. And then you can calculate the basic return on investment based on what is the margin improvement that you expect versus the cost that you incur. And you can calculate the annualized return on investment. So the point that I want to leave you with here is you can take literally data from companies' balance sheet, populate it with meaningful numbers for what might be the consequence of employing this approach towards smarter maintenance by employing condition-based maintenance, and inform the make informed decisions as management in terms of what will be the ROI. Okay. Now, these numbers will vary obviously based on the company, based on the sensing technologies that you pick and the operations, but the overall model will be pretty close. So, key summary. We presented our practical experience in terms of a possible way to think about how small SMEs and various levels of readiness can get onto the pathway towards smart maintenance and therefore smart manufacturing. You can take advantage of this framework by because it's much more personalized. It's not one size fits all. So the predicted performance improvements are very specific for the company at hand, so you can have much more confidence. It's not some apple pie, motherhood apple pie like thing which says, hey, if you employ this technology, you're going to get X% improvement in performance. No, this is personalized for the specific company. We tried it out with 3 companies, and we feel fairly confident that this kind of applied research has potential benefit for small companies in our region and around the country. And our analysis for company in a case study shows that it can be anywhere from, you can see 0 to 3% improvement in throughput. So depending on what the numbers are, that could be as high ROI as 26 to 1. So $26 for every dollar invested. So I'll stop here and take any questions that you might have. You can always reach me through PennTap if you have questions later, or if you watch the recording, and I'll try to answer the questions. If they're easy, I will answer. If they're harder questions, then my graduate students will be able to answer. So Amy, thank you for hosting us. I appreciate it. And let me know if you have any questions.
Okay. Taking a look here to see if we have any questions come in. We'll wait, just a short time. And obviously, as I mentioned before, everyone attending and registered for the webinar will receive this information. And if you have questions after the fact, our contact information is located on the slides so that you're able to contact either of us or send something to PennTap through the email pentap@psu.edu. And we'll make sure that we, get the information for you as quickly as we can. Let's see. Okay. Well, I think we can go ahead and move on and let the questions come in as needed after. So, again, thank you very much, Dr. Prabhu, for taking your time to talk with us, giving us some of your insights and obviously your expertise in the research that you've done. I want to go ahead before we conclude and let everyone know about some upcoming webinars with PennTap. On July 15th from 11 a.m. to noon, you can join us for the Act 129 Funding and Incentives to Finance Energy Improvements to Increase Facility Efficiency webinar. We will be discussing opportunities and incentives for small to mid-sized companies throughout Pennsylvania. We will have representatives discussing prospects for funding through First Energy Act 129 and the Department of Environmental Protection Small Business Advantage Grant. Additional funding prospects will be discussed by a PennTap advisor during that webinar. Join us again on August 19th for the Small Business Cost Savings and Energy Reduction Calculator Toolkits webinar, also from 11 to 12, where you can learn about simple, low to no cost steps you can take to make your building more energy efficient, more cost efficient, and more sustainable for the environment. PennTap has created a free energy toolkit as a starting place and guide to small businesses when estimating potential energy savings for your building. Be sure to visit the PennTap website to stay connected and be informed of upcoming PennTap news, webinars, and workshops. Thank you for attending today's webinar and have a great day.